Hello, this is Byron Washburn. I'd like to solve a problem using Lagrangian mechanics. I'm going to call this the tabletop problem. And let me kind of explain the problem. So what I have is a table. The table has a frictionless surface here. There's a mass of small m, and it's attached to a string. That string goes a distance rho to the center of the table where there's a hole. And then the rest of the string kind of hangs down, and there's a mass big M hanging down. Okay. So the little mass, or the mass little m, can rotate and change it can move in the xy plane, it can rotate and change its angle rho, or distance rho, with respect to the hole. But at the same time, the mass big M hangs the distance z below. So what I want to do is I want to get the equations of motion to describe the motion of both masses, little m and big M. So what we're going to do is we're going to start, so I'm going to use Lagrangian mechanics to get the equation of motion. Once I get the equation of motion, what I'm going to do is I'm going to look for equilibrium points and the frequency of small oscillations about those equilibrium points. So let's write down the equations of constraint for this particular system. One equation of constraint is that the mass, little m, moves only in the xy plane. So that's one equation of constraint. Okay. Second is the, so notice I have here distance rho, and then I have a distance z. If the total length of the string is L, then I get an equation of constraint that says that 0 is equal to L minus z minus rho. So that means that the distance z plus rho must equal the length of the string. And the final constraint is that the mass big M moves only along z. Can't move doesn't move x or y. So those are my equations of constraint. So then next thing I want to do is I want to write down the Lagrangian. So I need the kinetic and potential energies. So notice that this particular system it's a two-body system. There's mass little m and mass big M. So I have to write down the kinetic and potential energies for both of those guys. Now for the kinetic energy, what I'm going to do is say it's going to be the mass, it's going to be 1/2 the little m times its speed squared plus, we'll call that little m, 1/2 mass v big M squared, whatever that is. Okay. But you notice that the little mass only moves in xy plane, so we're going to choose a cylindrical coordinate system to do that. This guy here is going to be little mass times, it moves as, again, remember that v in the xy plane looks like rho dot rho hat plus rho phi dot phi hat. Okay, so that means that here, if I square that, I'm going to get rho dot squared plus rho squared phi dot squared. So that's the kinetic energy of the mass little m. The big mass only moves in the z direction, so that's just going to be equal to z dot squared, like that. Okay, that is the kinetic energy. The potential energy, what I have to do is I have to define a point of zero potential energy, so that's that. So then the potential energy, so the little mass, or the mass little m, has zero potential energy at all times. The big mass has potential energy mgz minus. So then that allows us to write our Lagrangian. Our Lagrange is t minus u. And what we can do is, so let's just write it. It's just going to be 1/2 m rho dot squared plus rho squared phi dot squared plus 1/2 big M z dot squared, and then we're going to be minus u, but minus u is going to be plus mgz. Okay, so what we can do is notice that there is a so what we can do is, okay, so that's my Lagrangian there. Okay, now notice that what we have is we have a z dot and a rho dot. But now what we can do is we can use one of the equations of constraint, and you can look at equation 2. Let me just kind of write it out here. So if I take my equation of constraint says this, okay. But if I take the derivative of that, that says that rho z dot is equal z dot minus rho dot, okay, is equal to 0. So that means that an increase in, so you got to be a little careful here. An increase in z is going to cause a decrease in rho dot. So that's an equation of constraint there. So then what that allows me to do is that allows me to get rid of the z dot and put in a rho dot. Okay, so that gives me this. So I have to be a little careful about, so if z increases, rho decreases. Okay, so let me take a look at that. Now, in the end, I don't care so much about signs because, notice I have this minus sign. But when I square it, it doesn't matter. So it basically says the magnitude of the speed, z dot, is equal to the magnitude of the speed, rho dot. Okay, so then that allows me then to get rid of the z's, okay, and then have, so that's good. Because right now I have actually 3 variables. I have rho, phi, and z. That makes it look like a 3-dimensional problem. I don't want that. This is really a 2-dimensional problem, and the 2 dimensions I want to have, 2 degrees of freedom, are going to be rho and phi. So then that makes this guy here, z dot is equal to rho dot. So then I can rewrite this as 1/2. I'm going to get m rho dot squared from that term there, plus, and then, well, actually, let me write it this way. So really, what I'm going to get, let me get rid of all this. I'm going to have 1/2. So from this, I get mass times rho dot. But from here, I get 1/2 big M times z dot squared, which is actually, so what I'm going to do is replace this guy here, not with z dot, but I'm going to write this as rho dot squared using this relationship that rho dot, or z dot, is equal to rho dot squared. So then that gives me here, instead of what I have, is that gives me little m plus a big M rho dot squared. Then I'm going to have 1/2 mass rho squared phi dot squared, and then mg, and then instead of z, I'm going to put here L minus rho, because I don't want z's, so I'm using basically the equation of constraint there. Okay, so again, I'm using the equation of constraint to get rid of z. Okay, so that's my Lagrangian. Now, if you take a look at that Lagrangian, you notice that the Lagrangian is a function of rho. Actually, let's write it this way. So Lagrangian is a function of rho, rho dot, and phi dot. Okay, but not a function of phi. That's important. That means that phi is ignorable or cyclic, and that means that p sub phi is going to be constant. That means that the angular momentum of the system is going to be conserved. Okay, so now what we can do is we can start off with that, and we wrote down what that angular momentum is. Okay, so let me so again, just defining a generalized let me write down the Lagrange. So Lagrangian here is going to be equal to 1/2 little m plus big M rho dot squared plus 1/2 m rho squared phi dot squared plus big M g L minus rho. Okay, so then let's start off there. So from this point, it's best to, let's write down that the generalized momentum. The generalized momentum, as we define, so this is P sub phi, okay? P sub phi, it's defined as the partial L respect to phi dot. Okay, that's my definition. If we just take that derivative, that's only that term there, I'm going to get M rho squared phi dot. That's what I'm going to get. So I'm going to define P sub phi as that. Now that is the angular momentum of the system. And so P sub phi, that's constant. And the reason why I know it's a constant is because, well, partial L respect to phi is equal to 0. that must mean that d dt from the Lagrange equation is equal to that is equal to 0. That must mean that this sucker, the rate of change of that, or well, actually, let me write it this way, is that d dt of p v is equal to 0. So that's where that comes from. Okay, so at this point, what we're able to do is now let's what we're going to do is we're going to now derive the equations of motion. So we have equations of motion for phi. In fact, what I have here are the equations of motion of phi. In fact, let's summarize that. So what I can say is that the equation of motions for phi is just going to be p rho. P sub phi is going to be equal to m rho squared phi dot. Okay, that's what I get there. Let me just rewrite. Actually, let me erase that. So I have that already. What I can do is I can just solve for phi dot. Okay, and then from this I get an equation of motion for phi dot. Phi dot is going to be equal to p rho divided by m rho squared. So that's my equation of motion for phi, or phi dot. Now you might say, well, what is p sub phi? Well, p sub phi depends on my initial conditions. Okay, what I'm going to do is I'm going to give this thing an initial rho and an initial phi dot, and then from that I can calculate p sub phi. That's just the initial, p sub phi is the initial angular momentum of the system, and that won't change. And again, you say, why doesn't it change? The reason why it doesn't change, think about the system. You have this mass here, little m. There is a force acting on it, but that force doesn't cause a net external torque on it. So since there's no net external torque acting on the system, then the angular momentum of the system will be conserved. Okay, so that's my one equation of motion there. What I'm going to do here, let's get rid of that for now. What I'm going to do is I'm going to write the equation of motion. So this is phi. Now what we're going to do is write the equation of motion for rho. So what I'm going to do is partial L rho. Okay. Well, you can see there's rho here and there's rho here. Okay. So I'm going to get from that m rho phi dot squared minus big mg. Just minus big mg. Okay, that's what I have there. Then I'm going to take partial L respect to rho dot. Okay. Well, there's only rho dot one place. That's going to be m big M rho dot. And then I'm going to take the full time derivative of that thing, and that is going to be equal to m rho double dot. So we put all that in the Euler-Lagrange equation, or the Lagrange equation I should say. Get m rho phi dot squared minus big M g. So that's this term here. Okay. Remember, by now you should know the Euler, or you should know the Lagrange equation, but the Lagrange equation is this in this case, d dt partial L respect to rho dot is equal to 0. So I'm going to put all that in there. This is the first term. The second term is going to be minus little m big M rho double dot equals 0. So I'm going to, well, that's it. Let me write it as a equation that looks like this. Okay. That's my second equation of motion. Now, take a look at this equation here. So you can see here, remember, this is a two-body system. This thing here looks like total mass times acceleration. And then this looks like a force. And then this guy here, well, let's say, well, what about that guy there? Well, what we can do is we want to rewrite that in terms of something that's conserved. And that's the angular momentum of the system. So what I can do is, using the equation I had before, instead of writing in terms of phi dot, I showed before that phi dot well, okay, what did I show before? Take a look here. Sorry, going back to here. V dot is equal to this thing here. Let's square it, okay, because I have a square in this guy. So V dot squared is equal to P phi squared divided by m squared rho to the fourth. Then I'm going to stick that into this equation here. Okay. Now if I do that, what I'm going to get is I'm going to get m rho double dot is equal to m rho, and I'm going to put this thing into there, p sub v squared m squared rho to the fourth minus big mg. Okay, that's what I have. And now let's just simplify things out a little bit. Okay, if I simplify this, I'm going to cancel out a couple rows in this. So here I'm going to get m rho double dot is equal to, and in here I'm going to get, the masses cancel out, so I get p sub v squared divided by mass rho to the third minus mg. Okay, now this whole thing here, it looks like the net force on the system. Now it's not really a force, so I'm going to call this net effective force. All right. Now this first term, that obviously is the weight of big M. Okay. Now this thing here is not really a force. Okay, it's not a true force. Okay. In fact, it has a name. This thing here has a name. And this thing, it's really a result of conservation angular momentum, but it has a name that you may be familiar with. It is called the centrifugal force. Now, the thing about centrifugal force is, first of all, notice there's a plus sign in there. That means it's an outward force. But centrifugal forces are not real forces. It is really a fictitious force. It's something that looks like a force. It's not really a force, but really, why is it there? It's there because of conservation of angular momentum of the system. So, but just because it's not a real force doesn't mean I can't treat it like a real force. So I'm going to define something called the effective force. And the effective force is going to be a sum of this centrifugal contribution, all right, plus the real force, call it that. Okay, so that I'm going to call that an effective force. Now, so since I have an effective force, when you think about it, okay, so this is an effective force, and what I can do is, even from this effective force, I can actually come up and talk about a effective potential associated with that force. So let's take a look at that. So here, what I showed is, okay, I have my effective force. Let's just, if I have a force, I can integrate it. And now notice the force doesn't depend on velocity or time. So this effective force, I'm going to get an effective potential from it by doing the definition of a potential energy is minus the work done by the force. If I just integrate this, I get this expression here. And so notice that here, this thing here looks like mgh, but then this thing here looks like something else. And then I can plot an effective potential from that. So then this term here, this 1 over rho squared does kind of this. The mg rho does that. And notice I have an equilibrium point there. So the effect of conservation of energy and conservation angular momentum gives me an effective force. And because of those two things working together, what I expect to get is I'm going to get an equilibrium position, and I'm going to get frequency of small oscillations about the equilibrium position. So let's find the equilibrium position and the frequency of small oscillations. So how do we do that? Well, we've done this before. So this is my equation of motion that I have here. My equation of motion is this guy here. The way I'm going to find the equilibrium position is set rho equal to rho naught, rho dot's equal to 0, and rho double dot's equal to 0. I substitute that in there, I get 0 is equal to this expression here. I can solve. Rho dot is going to be equal to the cube root of this stuff here. Remember, P sub phi is a constant. It doesn't change. Okay, so that equilibrium position will not change. It's just a constant squared divided by the mass times little m divided by the mass big M and G. That's a number for all times. Next thing I do is I'm going to find the frequency of small oscillations. I'm going to take rho. I'm going to make rho equal to delta plus rho naught. Delta dot equal rho dot, and delta double dot equal to rho double dot. Stick that back into my differential equation. Now notice when I do that is I'm going to get in the denominator rho naught plus delta. Now remember, at this point I'm eventually going to Taylor expand. So what I'm going to do is I'm going to factor out a rho naught out of this expression here. That gives me rho naught cubed, and then I get the quantity 1 plus delta divided by rho quantity cubed. So now that's my small thing. So I'm going to use the Taylor expansion. 1 over 1 plus x to the cube is approximately equal to 1 minus 3x, where x is a small thing. I take that and write it into there. That gives me 1 minus 3 delta divided by rho naught. Then I just start multiplying through things, okay? And in the end, what I'm going to get is so notice that here I have this times delta, this times 1. I collect terms that look like constant times delta, and then the stuff in here, this is from the equilibrium position. And so now I have an equation of motion that looks like this. Delta double dot equals a constant times delta equals 0. Now if you look at this guy, this will always be positive. Rho naught is, or P sub phi squared, okay, is a constant. Well, it's a positive number because it's squared, obviously. So everything here is a positive number. That makes this positive. So that means the thing will oscillate with simple harmonic motion with a frequency of small oscillations given by that right there. Okay? And that's what I expected. And the reason why I expected that was because looking at my effective potential, again, remember what the effective potential was. The effective potential was a combination of this so-called centrifugal-like term, which is really conservation angular momentum. This is a real conservative term. And then the combination of those two things create an equilibrium position. Okay? If the thing wasn't spinning, if the system was not spinning, then P sub phi would be 0, and then it would not have an equilibrium position. But the fact that it is spinning, has some initial angular momentum, has an equilibrium position, and this is why looking at an effective potential is really important. Okay, so we're going to do many problems kind of like this, okay? But so what's new here in this particular problem? Let me summarize. One of the main things about this particular problem is that this Lagrangian has no phi. That must mean that phi is a cyclic variable or ignorable. That means that the generalized angular momentum associated, or the generalized momentum associated with phi is constant. Back to real things that we talk about, that means angular momentum of the system is constant. Okay, so we use that constant through our equations. So this phi is, the Lagrangian is cyclic in phi, thus the generalized momentum associated with phi is a constant number. The next thing we did was we looked at the equation of motion. Okay, and when we looked at the equation of motion, we saw something that looked like mass times acceleration equaling to some net force. We identified this force as gravity, but this guy here, we gave it a new name. We called it a centrifugal force. We like forces so much it will make up stuff that looks like a force. It's not really a force. It is a result of conservation of angular momentum. But because of this concept is really important, what I can do is I can define an effective force. Thus, I can also define an effective potential. And from this effective potential, I can see that, hey, there's going to be an equilibrium point. Thus, I expect a static equilibrium point and frequency of small oscillations about that point. Okay, that's a very powerful technique, and we'll be seeing that quite a bit in class. We'll see you there. Bye-bye.